So that is this part. Then the next part of this discussion has this so-called alternate solution, and the discussion is a little bit convoluted in your text. And then finally you get the 9.1114, and which is like a integration of over the initial condition. And I mean, if the discussion in your textbook is, I mean, you can follow that, but it's a little bit more complicated than needed, in my opinion, because you can actually get that from this equation, the so-called alternate solution, actually exactly the same solution once you put this to here. Let's just, do I have time? I have maybe a few minutes, or try to see if I can get that. So after you substitute this into that, so you can write psi xt equals to, now that's a 1/2 square of 2, so add up to 1/2 pi. And then you have you have two integration. One is the integration over k. The other is integration over x after you put this in here. Right, and then now you have phi 0. But when you put it into here, you don't use the same x, because this is the integration variable. So like you can use x pi, right? And then you have this become e to the I minus ikx pi. But then you have the e to the ikx, right? So you have e to the, you have this a squared k squared t factor, and then you have plus I k x minus x pi. Okay, if that is, I think that's everything. Okay, so that is almost close to the form of your alternate solution in your textbook, except that the alternate solution has only one integration. Now you have two integration. So somehow you can actually integrate one of them out. But at first you need to do some transformation of variable, which is not too difficult. To figure that out, you can, one way to do it is do a complete square. So it's an exponential function of something, a function of k, but then you have k squared term, you have k term. You want it to be some just a square term. You don't want a square term and a linear term, because the square term you know how to integrate, just the Gaussian integral. You want to do a complete square. So let's just figure out what the complete square is. So minus a squared k squared e plus I k x minus x prime, right? What you mean by complete square is you want it to be a square term, like you get the square term out of it by, you can get the negative sign out first. And then you have a k, or a squared with t times k, right? That, I mean, finally you will square this, right? And the square of this, we cover this one, right? And then you wanted this one, 2 times this one times the other term, and the negative sign give you this one, right? So to do that, because you have minus I k x minus x prime in here, and then you need this times that to cancel this and that, and the factor of 2, so you have 2a t here, right? Like this times that, we cancel a squared of t, and multiply by 2, cancel the 2. What is left is I k x minus x prime. With a negative sign, but cancel with the negative sign. get back to this one, right? But then the square of this one, you need to cancel with that also. The square of that is you have I minus I squared is still -1, and cancel with the minus sign is a positive term. You will k squared, and then x minus x prime squared, and the other thing. But this is a positive term. You need to subtract that. Subtract k squared minus x prime squared 4 k squared. But that is that seems that we do it. So that is up. No. I at extra k, I don't need a k. So that's why you are confused. This time that we covered this one without a k. We just add extra k. So all right. So that's more like it. It's okay. Can you follow now? The square of that this, and then subtract this when we cover this one. Okay. And now that suggests change of variable. So I think this I would define that as c squared, like your textbook, c squared, because if you solve for that, so this is square, right? So x, it means x minus x prime equals to, or divided by this one is equals to c squared, or you can say multiplied by 2a squared of p is c, or x pi equals to x pi equals to x minus this one. Right. So that is you can see, right? And whatever that is, because c squared, that you can give it another name. Like this is eta squared, right? And so that is this argument in the exponential function, and this is dk dx. So we can now use all this new variable. I basically transform the variable from kx to a to c. Okay. And this one, this is right here. So 2 pi. There's a Jacobian you need to figure out. You have a d, this d to c, dA there. And there's a Jacobian, and then size 0. And substitute that the x prime is x minus 2a squared of t to c. And then the exponential factor is e minus eta squared minus c squared. Right? Now you can figure out this Jacobian. So eta is basically this one, right? So eta is, let's just write it down because we need to take derivatives, right? And c is basically this divided by this one. So, so the Jacobian is dA to d to c is Jacobian, not the Jacobian. Or you can say this 1 over j. But let's just figure out what to do, because that's not the j, so this is partial c partial. You have two variable, because a to x prime. C partial k partial c x prime. Yeah. And now figure out the Jacobian. A to k, that's a k, so a t, right? This one is going to this one, and plus a, the plus x pi is this one, so you get the I to a. As you can see, partial k, the basically that doesn't depend on k, that's 0. As you can see, partial x pi is 1 over 2a with a minus sign, right? But the Jacobian, we're using the absolute value. But, we talked about that before. The dk dx prime is whatever this dA divided by this one, which you multiply this times that is cancel 8 grab t. That's basically, this is minus 1/2, but when you take the absolute value, it's this 1/2 divided by 1/2 is basically a factor of 2. And so you need to multiply by a factor of 2, cancel the 2. And now this integral, size of 0 doesn't depend on a there. So you can integrate a there using a Gaussian integration, right? That would give you square root of pi, right? The Gaussian integral, just the a the integral, is square root of pi. So this will give you 1 over square root of pi. You can see size of 0, x minus 2a square of t, c into the minus c. Okay, so that should be your equation 9, 140. Right. That's how you identify the Fourier transform, right? Fourier transform, and then change a variable. You get back to the. So this is your initial condition size of 0. I think almost out of time, right? So whatever the size of 0x, now you shift it by this variable to a square of t times c, and then multiply by this one. It's okay. So a lot of step, but like I said many times, once you get a solution, the way to do it is substitute it back to the equation to see if it actually satisfy the solution, right? That's how you make sure that all this algebra you didn't make error. So this is how you get it finally. But finally, you can substitute it back to this equation and see if they satisfy that, right? And including the initial condition. The initial condition is easy to check because now initially t is 0, so set this to t is 0, so this size 0. That depends on x only, which is not involved in the integral. Then the integral you can see becomes a Gaussian integral. We get you square root of pi, cancel with the square root of pi, you get size 0x, which is the initial condition, right? So this solution satisfies the initial condition quite trivially. Now you put it back to the equation possible. I mean, the right-hand side is easier because second derivative. This one only depends on x minus something. So the second derivative is easy. So the right-hand side x squared also squared sine x squared. This substitute this into here. It's just get a squared. You can see. So I see a double pine. Pine is a derivative with respect to the argument, right? Because the argument is linear, depends on x, so that doesn't matter. Right, so that's the right-hand side. The left-hand side is take the time derivative. The time derivative only involved in this argument. So sine plus t is pi. You take the derivative, you take the sine 0 pi and take the derivative over this. So that will pull out the factor minus 2a squared of t. Let's see. No square root t. It's c divided by the derivative of square of t, which is 1/2 of square of t, right? That is the derivative. I see a point. Okay. Now to make this the same, so basically, suppose that you can do a integration by part. Let's see how to do it. You can pull out this, pull out all the factor out first. You have 2 and 2 cancel, minus a t. Right. And then, right. And the integration by part is you have, let's see. And size 0 point. Let's see. No, can see this as x minus. I'm running out of time here. And then you have the exponential function. Right. And minus infinity to infinity. And then you subtract the integration of just this one, because you're integration by part. So infinity, infinity, and which you get I take it back. Because integration by part is C, so that should be, you have this 2a, so everything else not good to be, because this combining with that is dd can c e minus can c square and divided by minus 1/2. Right. That, yeah, this is an integration. Right? Yeah. What do you mean? There's a minus 1/2. You take the derivative of that minus 2 can c, right? Either minus can c. Now you do the integration by part. I'm just too much out of time. That you have a size 0 pi, and then e to the minus square. You have minus 1/2, so that 1/2, and minus infinity, right? That will kill it, and then minus now you take a derivative of that. Size 0 pi, double pi, but then that argument has minus 2a t here, e to the minus c square. And now hopefully everything cancel. minus cancel. You have 2 and 2 cancel. But you get a square t, square of t, and square of t cancel. You have a square of t, a square of pi in here, and the rest is b can c. Yeah.